Hey everybody, let's have a look now at the basics of atoms and molecules. And you're thinking, Mr. B, I don't want to talk about atoms and molecules. I want to talk about brains and blood and bones and muscles. Well, these things are made of atoms. Ultimately, combinations of atoms and molecules that give us these structures. So in this brief video, we're going to look at some basics of atoms and molecules. And if you've had chemistry, you may want to skim ahead a little bit. Or if you need to review, and I'd recommend it, have a look and see if this helps you remember the differences between atoms and ions and elements and etc. Let's start with this. This is a gold ring. What makes up a gold ring? Well, atoms make up gold rings and make up me and everything you see on the screen. But what makes a gold ring gold is an element. An element is a particular substance with particular properties because of the atomic structure of what makes it up. So let's back up here a little bit. Gold happens to be, the gold element happens to have atoms that have 79 protons, 79 pieces, if you will, with positive charges. And there's also electrons and neutrons. If you have those things together, you get a gold ring. If you're looking at the guy in the corner of the screen, I don't have that making me up. So I don't have the structure and those properties. Let's kind of skim ahead to this. When we see the periodic table of the elements, what we're seeing here is all of these different combinations of atoms that can be put together to have particular elements. In other words, here, for example, is carbon, C. Okay, the carbon here is made of carbon atoms. These carbon atoms have 6 protons and 6 neutrons usually and 6 electrons. That's what makes carbon carbon, the combination of its parts, and in particular the protons. Nitrogen next to it is a different element. It has different chemical properties. It acts differently. The body treats it differently. It's still made of atoms, but these atoms are just slightly different than carbons. Oxygens next to it are just a little bit different than nitrogens. So when we see the periodic table of the elements, these are all pieces, if you will, that have particular chemical properties that all slightly different, they're different slightly in the atoms that make them up. If you think about what makes up a human, our total body weight, you see here that 4 elements, 4 of those combinations of parts, if you will, make up almost 97% of our body weight. As we mentioned in class, we don't get freaked out by oxygen being the highest one because oxygen is combined with hydrogen to make water. So when we think about our weight, a lot of our weight actually is in water. You also see calcium and phosphorus and potassium and sodium, etc. These again are going to be particular elements made of atoms, and we'll consider atoms more in just a moment. And each of these again has specific chemical different properties based on the atoms that make them up. Combinations of elements, as you may recall, these are molecules. So let's just briefly consider the parts of the atom, and I'm going to grab a pencil here. And recall, if you will, that an atom is going to have 3 basic elements to it. It's going to have protons and neutrons in the atomic center of the nucleus, and then orbiting these or passing around the atomic nucleus are going to be electrons. Let's just look at the 3 pieces here in terms of 2 things, their charge and their mass. Okay, electrons, as you may recall, have a negative charge. Protons have a positive charge, and neutrons don't have a charge, and that'll be relevant in just a moment. In terms of mass, in terms of how much weight, if you will, each of these has, we consider electrons to not really have any appreciable mass. Of course they have some, but it's so small and compared to other parts of the atom, protons and neutrons, we don't spend a lot of time talking about it. We just kind of assume it's about 0. And rather than trying to give you a weight of a proton in grams, we just say that it's 1, and we use a unit called 1 atm for 1 atomic mass unit. Neutrons also have 1 atomic mass unit for their mass. Okay, this is important because when we talk about ions and isotopes in just a moment, we're really cared about two things: their charge and the mass of the atoms that make up different elements. So again, if this is a review, great. If it's not a review, go back and watch this part again so you can know that, why electrons have a negative charge, why protons have a positive charge, and then ultimately how atoms can have different combinations of these. That'll be clear maybe in the next slide. So, let me grab my thing here. So, when we look at the periodic table and we have that big chart, we actually can read it for some different kinds of information. If you see the chart with some numbers and the letters here, the letters represent the atomic symbol. This is helium, and it's represented by He. Some of them are really obvious, like nitrogen is N, oxygen is O. Some of them, like gold, are not as obvious. Au, for example, it comes from the Latin meaning gold. But all of the letters on the periodic table stand for particular elements. The number at the top refers to what's called the atomic number, and that tells you how many protons that particular element has. And the number at the bottom is the atomic mass, which is a combination of the protons plus neutrons. So let's look at just two examples of how atoms can change and why that's important to us from an anatomy conversation. Most of the time, if you want to think about an atom being most of the time, it's going to be neutral, which means it's going to have the same number of positive and negative bits. What are positive parts of an atom? The protons. And the negative parts? The electrons. So normally, a neutral atom is going to have the same number of protons and electrons. So it has the same number of positive bits and negative bits. However, some atoms lose electrons. And if they lose electrons, now they're going to have more protons than electrons, and they're going to have a resulting positive charge. Just for giggles, let's say that this was 10 protons and 10 electrons, and let's say in our example, now we lose an electron, now we have 10 protons, and now we have 9 electrons. So, well, that should be a negative. So if we have 10 positive bits and 9 negative bits, if you even want to subtract them, we have a positive charge of 1. So if we have any positive charged atom, we call that a cation, or positive. And how do you remember that? There's a little plus in the middle of that. That little T is a plus, and that's how you remember that's a positively charged ion. It's an ion with more positives than negatives, so it's got a positive charge. If it were to, for example, gain electrons, if it was 10 positives and it actually picked up an electron, so now it has 11 negatives. Now it's got more negatives than positives, and now this is called an anion because it has an overall negative charge of 1. Why would atoms gain and lose electrons anyway? It gets into what's referred to as orbital shell theory. Don't sweat about this. It just so happens that sodium, because of the structure of its nucleus and the structure of the electrons that circle it, this becomes more stable if it can lose an electron kind of out here by itself. If that electron just takes off and goes to somewhere else, this structure is actually more stable for sodium. It doesn't do as much in terms of reactivity, and so this is a sodium ion. It's a, which one? A cation or an anion? It is a cation because it's got a positive charge, and that's what that little plus there means. It's got more positive bits than negative bits because it lost an electron, and therefore it's a positive sodium ion or cation. It so happens that chlorine, just because of the nature of its protons and electrons, is kind of looking for an electron to fill this last shell and to make it more complete. And so chlorine happens to be an element that picks up electrons pretty easily, and therefore it actually has more negative bits now than positive. It has 17 protons in here, but if you were to count all the electrons out there, it's got 18, and because of that, it has a net negative charge of 1. So ions are going to be hugely important when we get to physiology, because you'll see lots of examples of ions moving around in and out of cells. If you ever see an atomic symbol with a plus or an atomic symbol with a minus, then this means this is an ion. And of course you can tell the difference between cations and anions pretty easily. Okay, let's consider one other case where atoms can gain or lose parts. We didn't mention in the discussion of ions anything about neutrons, because the neutrons really aren't changing in ions, but they can change in this form called isotopes. So here we have carbon, and you see we have what's called carbon-12. It's called carbon-12 because there are 6 protons and there's 6 neutrons in its atomic nucleus. 6 plus 6 is 12. So that's why it's called carbon-12. And that's a very common form of carbon, to have 6 protons and 6 neutrons. Don't even worry about the electrons in this case. There is a form of carbon, though, called carbon-13, where you have 6 protons and 7 neutrons. So now that's why we have the 13, because we have the 6 protons and the 7 neutrons. So now this is a different form of carbon. And there's also carbon-14, C14, which has 6 protons and 8 neutrons with an atomic weight of 14. So we have here 3 different versions of carbon, but this is very important. It's still carbon. What makes carbon carbon is not the number of neutrons it has or even how much it weighs. It's really how many protons carbon has. Notice in every case we have 6 protons and 6 protons and 6 protons. Carbon is carbon is carbon, and the body treats it like carbon if that particular atom has 6 protons in it. Okay, so don't worry about this too much, because it may be a little disconcerting to you to look at the periodic table and see 12.011 and go, how can you get that? Because isn't that number the number of protons and neutrons? It is, but it's actually more of an average of, if we were to look out there in the world and if we could really count all the carbon-12s out there and all the carbon-13s in the world and all the carbon-14s and kind of add them up and look at the percentages, actually you see most of the carbon is in this form, but there's a little bit of this form and a little bit of that form. So if you were to do an average of all of the relative masses, it's going to be maybe not exactly 12. It's going to be a little bit more. But if you see 12.011, you know that that's probably going to be 6 neutrons, because you know the proton number is the atomic number. Okay? Can the number of protons change for an atom? If you were listening, you know the answer is no. If the proton number changed from 6 to 5, for example, it goes from carbon to boron. If it goes from 6 protons to 7 protons, it goes from carbon to nitrogen. So the proton number cannot change. If it does, it's a whole different element. And that's the difference here. Electron numbers can change and not change the element. Neutron numbers can change and not change the element. But if the proton number changes, it becomes something else altogether. So finally, one more look at the periodic table. Let me just show you a couple of examples here. If we look at nitrogen, nitrogen has got 7 protons. It's 14.01, so we know it's got 7 protons, and most forms of nitrogen have 7 neutrons. Again, we assume that nitrogen is going to be usually electrically neutral, so if it has 7 protons, it's also probably going to have 7 electrons. Okay, that was a semi-quick view of basic elements, basic atomic structure. When we get into class, we'll spend more time talking about how these things fit together into molecules and bonds. Make sure this makes sense to you. Have a look in your book if you need to. Once you feel comfortable, you can do the quiz on Blackboard. Thanks.